For being and thank you for staying with me. So the presentation is going to be split in 4 parts. Two first parts are about the company and the project we are launching today, and I will spend a bit of time explaining how we can use this R&D system of years and come to the conclusion on RFID and RF application. So quickly, who is Ardeje? Ardeje is a middle-sized company. The company has been founded 15 years ago, and our aim is to develop industrial inkjet printer from small scale, I would say 1 printed, to larger printed, 20, 30, 40 printed. Our key focus are in the industry, so really try to have a spectrum which goes from the lab with 1 printed to benchmark ink printed to large scale and big focus on the industry. We are also focusing on innovation. What I mean innovation is European project and country-based project or region-based project on different aspects of functional printing or graphics printing. And we have 2 ranges of applications. One is in the graphic industry for decorating objects, and the other one is on functional printing, maybe conductive, non-conductive, dielectric, solar cell, and so on. So maybe you have seen during tour in the exhibition the system we are launching, which is called Origin Dessin or Origin D100. It's an R&D system. We have only 1 printed inside. However, it's an industrial printed. The aim for this kind of equipment is really, if you don't know the printer you are going to use in the largest printer, you are going to develop ink. You are not sure about the recycling. You are going to develop inkjet coating for paper. You are not sure about the coating you are going to develop. You are going to test the interaction between the ink, the substrate, and the paper. And this is the kind of system you would like to have. This is a sort of data sheet we are going to use. Maybe you have a full flyer on the boat. The size is about an E4 format. The maximum speed is about 100 milliliters by second, and the accuracy is in the range of 1 micron. So what do we do with this kind of system? I'm here focusing on RF application. The system is somehow integrated in a workflow. And you develop RF application, then first you need to develop the antenna. So the first part of the workflow is software to design the antenna. They are going to give you size and dimension. The next step before printing is somehow using modeling of the printing, just to plot where the drops are going to fall and to make sure that the dimension and the size of the antenna you want to print is exactly the one you are going to get. However, software can't really solve all the questions, so then you need to go to the printing phase. Once you have the antenna, you have some parameter to adjust about the temperature profile, the sintering metal, maybe thermal, maybe higher, and so on. As the antenna has been designed with some dimension, some aid for the film off, you need the characterization. The next step is an echoed chamber to characterize the radiation pattern of the antenna. And then you go to the field with your antenna and you start to really characterize. Here is an example for RFID application. So the system we have been developing and the software to model the printer are part of a full workflow to make sure the antenna is really fulfilling the expectation. I'm going to speak about 2 European projects we have been involved in. I'm not going to develop too much the plastronic ones. It's RFID, it's already on the market, it's already existing, so there is nothing really new. However, on the giant project and emergent project are really new project. It's really based on innovation. The giant project is an acronym, and the aim is to replace the antenna you have for military application. And the emergent one is to develop Chipless tag. What you need to have to develop this antenna is to be able to print functional ink, and mostly is conductive inks, and make sure that once you have been printing those conductive elements, they are going to radiate, and you are going to measure those elements to radiate. So this is the first application. This is going to be light. This is the antenna soldier have. this antenna is dangerous and sometimes ineffective. When the soldier is going to lie on the floor, he is going to be lied on the antenna, and the antenna is not going to emit toward the sky, so he's not able to communicate. As well, the antenna is going to be touching his eyes and may be dangerous and harmful in terms of vision. So the antenna, the solution is either to integrate the antenna in the radio box or to have a remote antenna. So this is what we have been working on and we have been trying to develop. So here are two examples of the antenna we have been printing for this military application. The antenna is going to be put in the shoulder, so you have two groups of antenna, one for each shoulder. So two groups of antenna are composed of three monopoles, both on the side, and there is a cable running from the antenna to the radio post on each side. It means that when the soldier is going to lie down on one shoulder, another one is going to emit as well. So he's going to be able to communicate all the time. This is a radiation pattern, and the idea was a 360 degrees, 180 degrees radiation pattern in all situations, in all positions as a target. Then these are where inkjet starts and where our problems start as well. Because as I have been saying, the antenna is designed for a very specific dimension. Those dimensions does not take into account and the resolution and the volume and the spreading. So here the target is to superpose or to overlap and the design and some patterns you might see on the antenna which are part of the frequency you are going to work on. So these are some examples where we have been able to somehow manage to keep the dimension right, to keep the edge sharp, to keep the height enough to be able to radiate the different elements. Then, as I've been saying from the beginning in the roadmap, you need to be able to have some radiating element. If you have antenna all over your body, the power is going to be radiated outside and also towards your body. It means that you are going to receive a lot of energy, and this is going to be harmful as well for the soldier. The idea was to use some kind of interference, destructive on the outside of the antenna and positive on the outside. It means that the soldier, the body of the soldier, which is going to be there, is going to be somehow safe from radiation. So the level of intensity is going to receive is going to be below the SAR. That was as well another constraint due to the shape and the position of the antenna on both shoulders of the soldier. The next project I like to talk about is a project called Emergent. It's also an acronym, and it is about printing chipless tag. I'm pretty sure you all know chipless chip RFID. The idea with chipless is to remove the chip and to encode the information in different kind of antenna. Why is it useful? Sometimes it's difficult to have the QR code, or it's difficult to have a barcode, or you would like to have some redundancy between a graphics visual barcode and a non-graphic coding system. And this is where we have some assets to put forward as we've been able to develop and graphics and functional ink. What is the application for the chipless tag? One thing we are looking forward, and we think there is a market, is for EPC and UPC. I don't know if you are familiar with this kind of acronym. UPC is Universal Product Code, and EPC is Electronic Product Code. EPC, the aim is somehow to put an identity card for every object in the world. It means that you will have the manufacturer and the product type and the name of the product item. This is being coded in 9060-bit. So this is kind of workflow of the EPC for the project, for the product, from the company to the wider world where you are going to buy the product. And the idea here is to start to understand from a standard EPC and the coding capacity how many bits you need to code all the data. So the first EPC version are 64-bit and then 96 and a bit more. This is going to be quite interesting because depending on the kind of technology you are going to use for your chipless stack, the coding capacity is not going to be the same. And we are looking for at least 64, maybe 96 bits to make sure we can replace or at least have the same information on our chipless stack. So there are different coding, different strategy, and different coding capacity. Mostly, it's a frequency domain which is going to give us the highest coding capacity. And the principle of the frequency domain is, as it is said here, is to have one antenna per frequency. So you are multiplying the number of antenna up to 96 or a bit less to make sure you have all your coding capacity. So these are two designs of the antennas. As you can see on the left, the first one, there are 4 frequencies. What is interesting here is the size. It's about 50 centimeters by 30 centimeters for only 5 bits. In the recent publication, the last ones are for 8-bit and is about 6 by 7 millimeters. So we are going to reduce dramatically the size of the antenna to increase the coding capacity. Obviously, we need some high precision deposition system and somehow printers which are good enough, have high resolution, small volume to make sure we put exactly where we want to make sure we can manage those sides and those lines. The width of the line is about 200 microns. The spacing between the line is 300 microns. So it starts to be quite small even for inkjet and material deposition. The 2 next slide is to illustrate some kind of brute force approach of inkjet. Here is kind of imposition. Once you have designed the pattern and you put your pattern on the grid with a specific resolution, if the dimension of your antenna does not fit exactly a multiple of your resolution, you are going to increase or reduce the dimension without somehow knowing what is going to happen during the printing. This is going to have an impact on the frequency. And as we have seen, we are going to increase the number of frequency to code the information. We have to make sure they are all at the place we expect to. So those are some kind of artifact you are going to get. The width is going to vary. You are going to cut the corner. All of this is going to impact the frequency. So all what we have been developing as well as the printing system is what I would call a geometry-based raster instead of having a pixel-based raster. So it's all about dimension, being able to model where the drops are going to land, being able to model what is going to happen with the printing speed, and what sort of line you are going to get, what sort of roughness on the line you are going to get, to make sure that the pattern and the size you would like to get are the ones you have. The next bit is I've been able to code some information to my antenna. Another branch of interaction is about sensing. My antenna maybe could vary in terms of frequency with the environment. It means that if the humidity is going to vary, temperature is going to vary, or another parameter from my environment is going to vary, maybe the frequency is going to vary. It's kind of interesting to control those parameters. Let's say you are going to buy ice cream. The cold chain is going to vary. At some point you are going below a threshold. With this kind of sensor, we may believe there is a signature inside the antenna. So once you go above a certain point or below a certain point, the frequency is going to shift in some way or another, and you are able to check that you have a problem in the cold chain. So there are different parameters you could use, different liquid and materials you could use to either track temperature, humidity, pH, mechanical strength, or gas sensing. We believe that as well those materials, sensing materials, can be printed on the electrodes. So these are some examples, either from publication or from our own printing. So we have been printing the electrode. In this kind of sensor, the electrode, you will have the antenna here, as I've been speaking about, and you have some kind of electrode here. This is being printed here, this kind of sample I have in my hand. And you will print those sensing material on the electrode. And from the literature, the frequency is going to move one way or another, and you will be able to track temperature or pH. So I guess it's come to my conclusion. In terms of project and functional printing and antenna, as I've been showing, we have been able to print prototypes. We have been able to characterize them in closed environment, anechoic chamber. We have been able to characterize them in the field with solder, getting them in the equipment. The cost maybe of the ink is still a bit high to make sure we are going to print those tags everywhere with the graphics tag as well. We think that we need to have an intimate knowledge of the process. When I mean intimate knowledge, is really be able to understand how the ink is going to form, how the line and the pattern are going to form, to make sure the size and the dimension we are done at the modeling stage of the antenna are respected. And the last bit, and why it's come back to the graphic application, all I've been presenting has been about antenna with a fixed dimension. Now we can think about changing the size of the antenna as we are doing for variable data. It means that in the same way you do for barcode and so on, we could change the size of the antenna and somehow generating an EPC code on the fly, like variable data. So if you want to push the button and have some printing done, we are welcome to the bot. Thank you.
Thank you very much. Some questions. Can I ask you about the inks which you use for printing antennas?
Yeah.
Conductive inks. Were they silver inks?
Yeah.
So that was the reason for your point about the cost.
Exactly. Yeah. Exactly.
So apart from the cost, are there other problems with currently available conductive inks?
The problem is not so much with the ink as such. I mean, most of the problem comes from the height of the deposition. There is this kind of skin effect, as you may know. The current flows on top of the surface, depending on the frequencies. The deepness is 2 to 5 microns. So you need to print at least 5 microns. It might be a problem to put 5 microns in height when you have a width of 100 microns. So the limitation for that is maybe then it limits the distance you can read the tag because you don't have enough thickness for the ink.
Did you consider using a hybrid process where you print a seeding layer and then use electroless plating or electroplating to grow a thicker layer?
It has been considered. At the point where we are in the development in those applications, it's more about being able to design and print a full prototype in inkjet. Maybe the production way will be, as some have done in the past, to print a seed layer with copper or silver and then growing the thickness by another method. The idea is promoting full inkjet.